Hello everyone. So we start now. So my name is Owen. I am the developer relations engineer at Arm, and I am responsible for supporting APAC game developers. So today I will talk about Mali GPU architecture, including how the GPU works as a tile-based GPU. And recently, Arm just released Mobile Studio, which include three tools to help developers to profile their game performance and debug. So I will talk about it later, including case study. So first, for Mali GPU architecture. So our latest GPU architecture is Bifrost, and Mali G30, G50, and the G70 series are using Bifrost architecture, and is a unified architecture. So that means one shader core for vertex, for both vertex and fragment shader. And the number of shader core, as you can see on the picture, can scale from single core all the way up to 32 shader cores. And the layer is L2 cache to reduce the reader latency. Typically, it ranges from 64 to 128 KB per shader core. So this architecture is capable to write 132-bit pixel per core per clock. So on a A core design, it actually can write two 56-bit pixels per clock. And this is the block model of our shader core. In particular, in a picture, the black block is a fixed function block. And every shader core contains a execution core, which consists of 5 units. First one is execution engine. The execution engine is responsible for executing shader core and has a arithmetic processing power. And the execution core may contain multiple execution engines. It depends on which GPU you are using. And the load and the store unit is responsible for shared memory access, except the texture memory access. So it only for the non-texture memory access. And the varying unit is responsible for varying interpolation, and it also has the same arithmetic design of execution engine. And the stencil blend unit is responsible for the tile memory access. And the texture unit is responsible for the memory access to do with the texture. So it's separated from the load and store unit. So there are a few new features in Bifrost architecture. IDVS is one of them. Usually GPU will process all the vertex shading before cooling primitives. So, but often resulting in waste computation power and bandwidth for the vertices, which are only used in cooled primitives. So IDVS can split the your shader in two parts. One is for position shading before cooling, and one is for varying shading after cooling. By this way, we can save the computation power and the bandwidth. And it's done by driver and hardware automatically, so basically it's invisible to the developers. But as a developer, you can do something to make IDVS more efficient. If a developer can put position-related attribute into one buffer and the other attributes to another buffer, then the non-position attributes will not be pulled into the cache. So the cache can be store more vertex data. And the other new feature I want to mention is forward pixel kill. Although using RZ and the front to back rendering can remove most overdraw. FPK can kill the pixel thread in flight if we found the pixel will be occluded by another pixels. So the calculation thread already in flight can be terminated at any time. If we spot the later thread will write opaque data to the same pixel location. So let's look at the tile-based rendering. So traditional desktop GPU architecture usually use immediate rendering mode. So that means vertex shader and the fragment shader will be executed in sequence on each primitive in each draw code. So here is the pseudocode for the immediate rendering mode, and you can see the fragment is right after the vertex shading. Okay, and this picture shows the traditional immediate rendering mode pipeline. And you can see there are a lot of external here. There are a lot of external memory access at the fragment stage. For a mobile device, this kind of external memory access is quite bad for energy efficient. So most modern mobile GPU use tile-based rendering mode. It is designed to minimize the amount of the external memory access which are needed during rendering. So the tile-based renderer split the screen into small pieces. The tile size we call it a tile. The tile size of Mali renderer is 16 by 16. And the GPU will process fragment shading on each small tile. Then write the result out to external memory when the tile is finished. So one big difference from the immediate rendering mode is that the GPU will split each render path into two distinct processing passes. One is a vertex shading path, and it will generate the tile list. Then the other one is a fragment shading path, which will execute fragment shading tile by tile. So that is the pseudocode for tile-based rendering. The GPU will execute the vertex path first for all primitive in one render path, and finally generate a tile list. Then GPU will execute fragment path for each render path, tile by tile. And this picture shows the pipeline of tile-based rendering mode. As you can see from the picture, tile-based rendering move the memory access to the tile memory instead of external memory, and this is much faster than energy efficiency. One thing I need to mention is that there is a extra memory access here to extra external memory read and write access for the tile list, which immediate mode GPU doesn't have. So extra geometry paths on mobile device is usually more expensive than on desktop. And then I am going to talk about render path. It's an essential concept for tile-based GPU, and no such thing on desktop GPU. So render paths are essential for tile-based renderer, and is a single execution of rendering pipeline, and rendering a single output image into a set of frame buffers. So each render path needs initialization in tile memory at the start of the render path, and writing back to external memory at the end of the render path. So to get the most benefit from the tile-based rendering approach, it is critical that applications, that means your games, need to minimize the amount of memory traffic into and out of the tile memory. A tile memory is a fast run on chip. So that means avoid reading in older frame buffer values at the start of the render pass, and avoiding writing out value at the end of each render pass. So here is an animation, show you how tile-based GPU works. So primitives rendered, you send the primitive you send it to GPU will do the position shading first. After position shading, the primitive will need to pass the facing test cooling. And any back-facing primitive will be cooled here. And the next one is frozen cooling, test cooling. The primitive outside the viewport are cooled here. Then go to the sample test cooling. Any primitives which are smaller than 1 pixel will be cooled here. Then finally, all survived primitives can do the varying shading, then add it to the tile list. So after the vertex pass of the render pass is finished, GPU can run the fragment pass. The rasterizer will rasterize the primitive into quartz, which is 2 by 2 sized. Then quartz need to do the early Z test before going to the next stage. But if the fragment is using discard instruction or using alpha to coverage or writing the depths in shader, the quad will skip early Z test and do the later Z. Early Z test will kill any quad which is fully occluded by other pixels. After early Z, a fragment thread creator will create 4 fragment threads for a quad. Then the fragment thread will be dispatched to execution engines. And for those fragments cannot take advantage of early Z test, will done later Z test will be done here to kill the fragment which are occluded. Okay, finally the survived fragments will do the blending, then write to the tile memory. After all primitive in the tile list have been finished, the tile writer will write the tile result back to external memory. Memory has a transaction eliminator which can compress the tile result, writing back to external memory to save the bandwidth. So, but OpenGL API, OpenGL ES API has no explicit render path in API level, right? So the driver must infer which rendering operation from a single render path. So how the OpenGL ES driver from a render path? Basically, driver will add a drawing comment to the current render path, and the render path is submitted for processing when an API code change the frame buffer or force a flush on the queued work. So here I list the most common calls for ending a render path. Whenever you call those APIs, the driver will end the current render path immediately and submit it to GPU. So now we know how render path works. How can we write a code for efficient render path? There are a few things you can follow to make sure you write the efficient render path code. First, processing each render path once. That means binding each frame buffer object only once. Don't switch frame buffer object back and forth, and making all required draw code before switching to the next content, and avoid unnecessary context switch. So second, you should minimize the load from last frame buffer at the start of the render path. There are two ways to avoid the tile load. First is using clear, GL clear function to cheaply initialize the tile memory to a clear color value. And the second one is using GL invalidate frame buffer function to hint driver don't load the data from external memory. And third, minimizing the store to the frame buffer at the end of the render path. So avoid writing back to main memory whenever it's possible. You can notify the driver that an attachment is actually a transient by marking the content as invalid using a call to GL invalid frame buffer as a last draw code. So let's talk about on Mobile Studio. Mobile Studio is a new tool set we just announced this year, and it contains of 3 tools: Streamline, Graphic Analyzer, and the Performance Advisor. And the starter edition is free of charge, and you can actually download it from On's website now. It fully supports 32 and 64-bit CPU. The tool can access to detailed CPU and GPU hardware counters and do the frame-by-frame analysis of OpenGL ES and the Vulkan content. And you can use the tool to enhance your profiling experience with custom code annotation. And this tool works on unrooted device now. So you don't need to root your device anymore. So then here is a link. You can download the Mobile Studio. Okay, Streamline, I just do some quick introduction for all tools. Streamline is a tool for performance profiling, help the developers to find out the bottleneck of the performance. And the Graphic Analyzer is a GPU API debugger. It captures all data and the rendering a frame, and the developer can check the API codes one by one to debug a frame. And the Performance Advisor is an automatic analyzing tool. It can generate an analysis report to give you a performance overview quickly. So, but it's not released yet, but we will release soon this year. So let's look at Streamline. Streamline basically can sample the application and collect performance counter from hardware, and no matter what graphic API you are using. And the developers can use Streamline to find the potential information bottleneck. Besides collecting hardware counters, the user can also define their own custom counters driven from the hardware counters. I will talk about how to do it later. And the developer can also add a Streamline annotation from your source code. So because there are so many hardware counters and I have no time to cover them all today, you can check the information of hardware counters on our website. And this one is for old architecture Migar, and this one is for new hardware Bifrost. Okay, today I will give you a case study of profiling a real mobile game using Streamline. So I will show you the numbers I got from Darkness Ray 3 and show you how to analyze those key numbers. So this is the frame rendering step by step I captured using graphics analyzer, and I collect the counters from this screen. And you can see it's basically rendered from front to back. So that's good. And so Besides collecting hardware counters from GPU, Streamline also have a few features you can help you to analyze the data quickly. So first, you can load built-in template. We have a built-in template chart to help you analyze key numbers quickly. And there are a few built-in charts for different managed GPU, and you can choose template from the drop-down menu, like the here shows. Okay. And you can also create, if the template is not enough for you, you can also create your own chart set to analyze the key numbers you care about. And you can save your custom chart set as a template. And so next time you can just load your pre-created template. The chart set on right hand side is my own set. This one is my own set. And I usually will use this set to do the best performance analysis. And you can also create your own expression to get any driven number you want to look at. Like this picture shows, that's the expression you type in, and you can driven your own counters from original hardware counters. So it's quite useful. And I usually will arrange the chart from big picture to details, and this arrangement helps me to find out the performance bottleneck step by step. So I will go through all the chart here. Okay, so usually you will need to look at the utilization of two workload first, compute and the fragment workload. From the utilization numbers, you will have the idea how parallel the GPU is working. So from this chart, we can see some problems in yellow rectangles here, and here. There are many pipeline bubbles, and that means fragment and the vertex shader are not running in parallel. Sometimes you can see there are some gaps. Okay, and from the GPU chart, this one GPU chart, you can also see the GPU is not always busy. The red rectangle means the GPU is idle, so it's not always busy. So the picture shows the chart and the expression I used. That's the expression I used to get the counter. Okay, so from the chart you can see GPU utilization is only 40%, and that means the application is actually not GPU bound. So when GPU is not always busy, we need to look at the frame per second. Since the frame per second is about 50, we can tell the gain is actually CPU bound. Okay, so we can see the compute and the tile utilization are all about 16%, and the fragment utilization is 80%, 87%. So we can tell the application is actually fragment dominated. So, but in real case, you need to fix the GPU bound first until the bottleneck move to the GPU. So you should not see, you would not see any improvement if you optimize GPU pipeline for a CPU bound application. So this one is about the shader unit utilization. Then we can see from the chart the textual utilization is about 63%, which is higher than other unit utilization. So the second one is execution unit is about 49% busy. So when we are going to optimize this game, we should focus on these two units for optimization. Okay, the bandwidth chart, those numbers can show the bandwidth requirement of the application. So the total bandwidth requirement is for this scan is about 2.7 gigabyte per second. So this number is quite high for mobile device, and keep this number under 2 gigabyte per second to get the best balance between performance and the power consumption. So the shader, the other one is the shader read cache miss rate is about 40%. So this number doesn't include the texture reading. So if you want to lower this number, you can optimize, like you can optimize index buffer to get benefit from cache, or you can also use a smaller vertical data buffer to get benefit from cache too. For example, when rendering a shadow map, you may only need a position attribute. You don't need a texture coordination attribute. So you keep your data smaller. So pointer is keeping the data as small as possible to get benefit from the cache. So this one is about the cooling here. We can collect some numbers to know how the primitives has been cooled before rasterization. So we can get a back-facing cooling rate here. Any number around 50% is healthy. Otherwise, the application may need to check the back-fast cooling setting. You can also use graphical analyzer to check it if necessary. So, and the frost cooling rate shows how many primitives has been cooled by view frosten. So 2.1% means most invisible primitives has been cooled by application before sending to the GPU. So it is good. And the sampling cooling rate shows how many primitives are cooled because they are smaller than 1 pixel. So it is a good hint for micro geometry issue. From the number we can tell about 44% primitives are smaller than 1 pixel, and this number is pretty high. And in this case, the developer may want to use the level of detail mesh to lower this number. And rendering a pipeline which cover less than 10 pixels is really bad for performance. So keep the triangle big enough. The total visible rate after fast cooling is about 55% for this scan, and that means almost half of primitive sent to GPU is invisible. So it's kind of a waste of the bandwidth. And in this case, too many small triangles. So here is the IDVS and the varying chart. IDVS varying rate shows how many varying shading requested against the position shading. So we can see there are 64% vertices which do the position shading then cooled. And the other number shows how many varying are 16 bits. In this case, only 17% varying is 16 bits, and 83% varying are 32 bits. So remember, 16 bits varying interpolation is 2 times faster than 32 bits varying. So we suggest the developer to use 16-bit varying whenever is possible. So in this case, the developer need to look into the shader code and optimize it by removing unnecessary 32 bits varying. So this chart is about early Z. Early Z update shows how many quartz which pass early Z test have update depths and stencil values. From the chart, we can see about 27% quartz cannot do update and will go to let Z. And to send as many quartz to early Z as possible, The shader should avoid using discard, modify the depth value in shader, and avoid using alpha coverage. So this chart is about micro geometry. So in previous chart, we got sampling cooling rate, which is 44%. And in this chart, we got partial fragment rate. This number can be used as a hint of microgeometry issue too. So when this number is high, the application may render too many microgeometries. So we can also use expression to get the amount of pixel per primitives. Any numbers under 10 will be an issue, but since the number pixels per primitive is an average number, sometimes it will mislead the analysis because one huge primitives with some small primitives may result in a good average number. So you better use a graphic analyzer to double check it. So let's go to the overdraw chart. We can use expression to compute the fragment per pixel and the fragment cycles per pixel. So fragments per pixel can show you the overdraw issue. In this case, it's 1.3. That means a pixel will run 1.3 fixed fragment thread. So it is healthy. So there are not many overdraws. So and FPK as a forward pixel killing rate is low here. If the number is high, you may need to check your object sorting and keep rendering from front to back for opaque object whenever it's possible. Okay, so about the occlusion, you can use instruction diverge the rate to check if your gain has too many flow control divergence of the shader. Higher number means more fragment thread has been masked out, and it is better for performance because the GPU will compute all the possible results and mask out the other one and choose the correct one. And texturing. So from this number, we can see all texture in this game use compression format. And since bandwidth on mobile device is a scarce resource, we suggest the developer always use compressed texture format. And the texture cycle per instruction is 1, and it is healthy. We can see from this number, the application doesn't use expensive texture filtering like trilinear or isotropic filtering. So, and the texture read cache miss rate is about 48%. If you want to improve this the cache hit rate, there are a few suggestions. So, first, you can use proper size texture for mesh. Do not use a big texture on small mesh. And you should use mimap whenever it's possible. And use a smaller texture format like ASTC. And use a smaller isotropic level. And when you do the blur effect, maybe using smaller filter kernel size in shader. So that's a chart for L2 cache. From those numbers, we can tell a few things. First, it's a vectorization rate is low. That means most access request is not full-size data access. In this case, we need to look into shader code to optimize the data access because we have two kind of data access: is full-sized and short. And if you use a lot short data access, you will actually read the full-size data, then discard the part. So that's waste of bandwidth. And they are about 4% external memory read latency is higher than 384 cycles, and the memory read latency over 384 cycles should be considered as an issue because the GPU will idle to wait for the data return from the external memory. So let's check this picture. There are many catalogs about the latency, and the final one is the latency you should avoid. Okay, the final one is about latency. This chart is you can know how many fragments cannot take advantage of RDC, and how many fragments which go to the latency and then be killed. So that's kind of waste of the shading power. Okay, if the latency test rate is high, and that means many fragments cannot take advantage of RDC. And in this case, need to check the shader code and the render state setting to remove those operations which will cause RDC disabled. And if latency kill rate is also high, that means the GPU has wasted power on many invisible fragments. That's the thing you will try to avoid. Okay, let's talk about the streamline annotation. Streamline annotations let you instrument your source code by adding annotations to it. It is written in C++, and we implement a C# wrapper, so the developer can import it as a Unity package now. But to use the streamline annotation, you need some setup for your Unity project. First, you need to make sure you are using IO2 CPP as the scriptable backend. And the second, you need to set C++ compiler configuration to debug. And the third, set the target architecture to ARM64. We are currently supporting ARM64 only. And finally, you need to build a development build APK. And there are three types of annotations. First is the marker, is the simplest form annotation. It is just a single point in time which a label that will appear at the top of a streamline timeline view, like this one. That's a marker. As you can see from the picture, the green label on the top are the markers. And the second one, this one is a channel. Many annotations can be placed into a channel. And unlike a marker, each annotation spans a range of time. You can see it can measure the time you spend on a task. So you can use it to mark the total time the gain spent on some operations. On this picture, the yellow and the blue label represent the different annotation in the same channel. And then the final one is custom activity maps, which are the most advanced form of annotation. You can think it as a structural map, which many channels like the picture shows. So you can group as many channels as you want into one map. The map will appear as its own view in the lower half of streamline UI like the picture shows. So your custom map will show here. And you can insert a lot of channel inside the map. So you can download the Unity package here. Okay, so about the graphic analyzer. This is a graphic analyzer. The core of this software is the trace view. Oh, sorry. the trace view, and it contains all API calls. They can be literally millions for complete application. You can see. Sorry, I just here. Here is the trace view, and this is why we have built in an outline view here. Outline view shows all the frames and the draw codes that are rendered. And we can select any draw code or in fact any API code and see the state of the application at any point. And the graphics analyzer offer full visibility of GL state and asset, including vertex and fragment shader, and the texture and the buffer, uniforms, vertex attributes, but the most useful feature is probably the frame capture, because it can help you to analyze in detail a frame to understand how it's being drawn, and help understand if the draw code can be optimized, removing lane or reducing vertices, and help understand if the order of the draw code is optimal to reduce overdraw. So outline view shows all the frames and the draw codes that are rendered, like here. And it will show the render path actually happened in driver, because when you write your code in OpenGL, you actually don't know how many render paths you will create it. So you can see from here how many render paths for your game. And after you select a draw code here, you can see the detail API code here. So investigating at a frame level. So find out what the draw code have higher geometry impact. You can find out here. So this window shows contents of uniform and the vertex attributes for each draw code. So when a draw code is selected, all the associated data is available. So uniform tab can show uniform values, including sampler, matrix, and arrays. So you can debug here. And the vertex attribute tabs will show all the vertex attribute, their name and their position and the data. So you can also view the rendering mesh in 3D here. So this is quite useful to debug a graphic issue. So shader reports and the statistics window is also very useful. All the shader being used by application are reported, and the shader are compiled with many offline shader compiler, and report the number of instructions, number of work registers, and the uniform registers. So additionally, how many times the shader has been executed can also be reported here. So frame capture and analysis, and a native resolution snapshot of each frame buffer is captured after every draw code. So this capture is actually happened on real target. So even a target-dependent box or precision issue can be investigated in graphic analyzer. Okay, and the graphic analyzer also has few different drawing mode to help you debug the application. The first one is the native mode. It will render with the original shader. And second one, in the middle, is overdraw mode, with the highlights where overdraw happens. And then the final one is shader map mode, will show each shader with a different color. So it helps you to identify the particular shader. Okay, so there are more resources you can find on our website. If you are interested in Vulkan, you should check this link. There are many useful information and samples. So here is my email and the general support email for developer. So you can send us your question or issue regarding to Mali GPU anytime, and we are very happy to help you. So let me. Is there any question?
그 저 툴이 혹시 안드로이드 OS에서만 작동하는 건가요? 아니면 아이폰이나 다른 플랫폼에서도 작동하는 건가요? 그 새로운 그, 그 모니터링 툴이.
Is only for Android and Linux, I think.
아,
Yeah.